Hello, my name is Victor and I study Material Science and Engineering at the University of Illinois at Urbana-Champaign. Over the past few years, there's been a growing concern over climate change and resource depletion, and so researchers are currently examining ways in which to make the construction industry more sustainable, given its known consumption of large quantities of materials and energy, while producing considerable amounts of emissions. In particular, concrete production is responsible for large emissions, which contribute to climate change in a variety of ways. Researchers at New Mexico State University have been investigating the use of novel materials, which could eventually replace the currently used concrete masonry units, or CMUs. They are developing a composite material which is made of traditional adobe mix and reinforced with sisal fibers, which come from the agave family, for increased strength. My role in this project was to determine through a quantitative study whether the proposed composite was more sustainable than concrete masonry units. In order to do so, I performed a life cycle assessment, which is a standardized process to quantitatively analyze potential environmental impacts associated with a given product or process, as examined in a cradle-to-grave perspective. This means that the entire life cycle of the functional product is analyzed from the moment that all of the raw materials involved are extracted from the environment until they are all returned to the environment, either in the form of waste materials or emissions. And so we track all of the processes involved during the product's life cycle, then we quantify the emissions associated with those processes, and finally we assign those emissions to indicators of potential environmental impact, such as global warming potential, acidification potential, etc. The first step was to define the functional unit. A functional unit is defined such that the product comparison is based on the same functional output. In our case, we defined our system to be a 12-foot tall by 1 foot wide wall section with a structural capacity of 34,000 pounds or greater. All of the calculations hereinafter are based on the production of this functional unit wall section. In order to create the life cycle diagram, one must study all of the processes involved in each of its phases, which include materials acquisition and processing, product manufacturing, product use and disposal, by reviewing a variety of government documents, peer-reviewed journal articles, and industry documents. The next step was to create a life cycle inventory, which consists of large data sets with all of the energy and material inputs. Those material and energy inputs were estimated with the help of NMSU researchers, as well as, again, a variety of documents. Once we have the life cycle inventory, we can use computer modeling and LCA databases found in Gavi to collect all of the emissions associated with the given materials and energy inputs. Finally, we can perform an impact assessment in which we can categorize those emissions based on potential environmental impacts by converting to the appropriate units. Our results indicate with clarity that this sisal reinforced adobe composite has considerably larger potential environmental impacts throughout all of the categories. In order to determine and interpret those results and examine the source of such negative environmental impacts, we broke down the emissions according to the material components which make up the reinforced adobe wall, as well as a CMU wall. And we found out that 88% of the adobe emissions stem from the production of sisal fibers alone, which constitute less than 1% of the material. Further investigation into the cause of those emissions led to the conclusion that it was the required use of large quantities of nitrogen fertilizer during the cultivation of sisal which account for the vast majority of those emissions. Our conclusions were, first, that a sisal fiber reinforced adobe wall has a larger potential environmental impact than concrete masonry units, assuming fully industrialized processes. However, if sisal fibers are replaced with a different fiber reinforcement with less emissions but similar mechanical properties, the adobe composite would likely provide a sustainable alternative to concrete masonry units. And finally, the importance of sisal cultivation in these findings demands a more thorough study into those processes involved. Thank you for listening, and I hope you enjoyed the presentation.